Hello everyone, welcome to today's class on heat energy, the continuation of our preparatory classes for the end of school exams. We're going to be looking at heat energy with a view to looking at heat capacity, specific heat capacity, and latent heat. Many of these things are things we've heard before, just by way of a reminder. So let's lay a background. First things first, what is heat? Heat is a measure of the internal energy possessed by a body, and heat moves from a hotter region or body to a cooler region or body. Heat is also a form of energy, and like all forms of energy, its unit is the joules. And also, like all forms of energy, the law of conservation of energy holds true, which means that energy cannot be created or destroyed. So the total energy lost by the body losing the energy must be equal to the total energy gained by the bodies gaining the energy. For instance, total electrical energy lost by an electrical heater must equal total heat energy gained by water plus the total energy gained by the container in which the water is. That is the whole essence of the law of conservation of energy. Energy lost from one body is gained by another body. And that is what this topic is about. So let's understand the concepts again. First, heat capacity, also called thermal capacity. That is the quantity of heat required to change the temperature of a given mass of a body by 1 degree Celsius or 1 Kelvin. Is the amount of heat energy required to raise the temperature by a unit. And this varies for different substances. Some materials will require more heat before they can have a temperature increase of 1 degree Celsius. Some require less heat. Those that require more heat are said to have higher thermal capacities than those that require less heat. And our thermal capacity, the symbol is C, capital letter C. Please take note, it's different from small letter c, which means something else. Capital letter C is the heat energy Q over the change in temperature, as you can see on your slide. There's a question here that you should try. So you can pause this video at this point and try this question using the formula given above. Now, let's look at specific heat capacity. That one is given by small letter C. The word specific refers to a unit. So when you hear specific density, it refers to density of a unit mass of a substance. When you hear specific heat capacity, it also refers to a unit of anything that you are referring to. So in this case, SHC refers to the amount of heat required to raise a unit mass of a substance by 1 degree rise in temperature. And for clarity, a unit means 1. So to raise one mass, whether 1 kilogram or 1 gram of a substance, the heat you need to raise that mass by 1 degree Celsius is what is called the specific heat capacity. And it's given by the formula Q equals MC, change in temperature. The delta there stands for change in temperature. Q represents heat energy. Some other textbooks or examiners will use H. Whichever letter you decide to use will be correct. Capital letter Q or capital letter H. There's another question here also that you may want to try. Pause this also and try using the formula given above. Let's look at a sample question. It's right there on your slide. You have a block of metal of mass 1.5 kilogram, which is insulated and is heated from 30 degrees Celsius to 50 degrees Celsius in 8 minutes 20 seconds by an electric heater rated 54 watts. Find the quantity of heat supplied by heater, the heat capacity of the block, the specific heat capacity. Now, what we said about conservation of energy works here again. The heat that is being gained by the metal is the heat being lost by the electric heater. So for you to know the heat gained by the metal, you must calculate the heat that is lost by the electric heater. And the form of energy that we have in electric heaters is the electrical energy. And that is given by the formula IVT. or PT, since IV is the formula for power, electrical power anyway. So from what you can have on your slide, the A there gives us 27,000 joules. That's by multiplying 54 watts, that's the power, by 500 seconds. Someone will ask, how did I get 500 seconds? You have to convert your 8 minutes, 20 seconds into seconds. So all the time must be in seconds. 8 minutes, 20 seconds. If you convert that to 20 seconds, you get the 500 seconds that you're seeing on the slide. And then for the B part, we are asked to calculate the thermal capacity. From the formula you used earlier, that's the heat energy divided by the change in temperature. You get the answer as it's on your slide. And then the specific capacity also using Q equals MC delta theta. Makes use of the formula, you get the answer as it is given on your slide. You may also want to pause and then walk through that question by yourself. There's also another question here that I would also be solving for us. That is heat loss by hot water equals heat by cold water. The solution is also on your slide. You may want to also look through it again by yourself. Now, the temperature here that we have, initial temperature of water is 70.0 degrees Celsius. And then the final temperature, it was added to a temperature of water at 100 degrees Celsius. You are asked to calculate what the final temperature of the mixture is. The solution is right here on your slide. Go through it. It's the same method. Heat lost by hot water is equal to heat gained by the cold water. So in this case, we are using heat loss equals heat gain, MC theta, MC change in temperature in both instances. Boss, do it by yourself. Your final answer should be 30 degrees Celsius. Now let's go to latent heat. Matter exists in 3 states: the solid state, liquid, and gaseous state. Now, when a change of state is occurring, you don't notice a visible change in temperature. So it seems like you are not really absorbing or releasing heat, but you are. Just that the heat being absorbed or released is not resulting in a change in temperature. Rather, it is being used to break down the bonds or to bring the bonds closer, as it were, depending on what state you are transferring from and to which state you are transferring to. So latent heat refers to the heat released or absorbed at constant temperature. Constant temperature is key. When you deal with latent heat, there is no temperature change. Matter changes state at constant temperature. The diagram here is just to show you some changes of states of matter that we have. Solid to liquid is melting, liquid to solid is freezing. These are basic things that we'll know. Look at the diagram again for better understanding. Now let's look at, as we said earlier, the word latent means hidden. Latent heats do not show their presence in terms of a visible change in temperature. Rather, they are used in changing the state of matter. Now, we have 2 kinds of latent heats. We have the latent heat of fusion and latent heat of vaporization. Latent heat of fusion has to do with matter changing state from solid to liquid or from liquid to solid. Latent heat of vaporization has to do with matter changing state from liquid to gas or from gas to liquid. Latent heat is needed to change a substance from a solid to liquid or from liquid to gas. And the amount of the heat that will be needed will depend on the mass of the substance. Now, let's look at specific latent heat. Just as specific heat capacity, the word specific here also refers to a unit mass. So specific latent heat of fusion will be the amount of energy needed to change a unit mass of a substance from solid to liquid without a change in temperature. The specific latent heat of vaporization is the amount of energy needed to change a unit mass of a substance from liquid to gas. It could as well be from gas to liquid without a change in temperature. And the SI units for latent heat is joules per kilogram. Joules per kilogram. You can see that there is nothing like degrees Celsius or Kelvin there. That's because temperature is not factored in during latent heat. The heating curve that you have on your slide, as well as the cooling curve show you different things that happen when matter changes state. The flat horizontal lines you can see are the processes of change of state of matter. So pause the video, look at both curves, the heating curve and the cooling curve, and you'll be able to understand better what is happening there. Now, solve examples. A heater which supplies heat at a constant rate of 1000 watts is immersed in a 3 kilogram block at 0 degrees Celsius. Now, the block takes 1020 seconds to melt completely. Calculate a value for the specific latent heat of fusion of ice. In this case, the total heat lost by the heater, which is electrical energy, IVT, is equal to the heat used by the ice in changing state, MLF. LF there is a term. LF means latent heat of fusion. So in this case, because it's change of state, there's no temperature difference. Temperature will remain constant. And then using your equation, IVT equals MLF, you will get your LF as the answer given here, 340,000 joules per kilogram. You can also do it by yourself. The second question here is for you to try. So pause this video and try question 2. If you do it well, you should get the answer given there, 45,000 joules. Now, that is the end of our lesson. You have your assignments, which I will also expect in the next 48 hours to my email, david.oluwadara@olashoreschool.com. david.oluwadara@olashoreschool.com. So do the questions you have, apply all the formulas that you have been given in this presentation, and then we will meet again to have a review of your work. Thank you and have a nice day.